Okay, last example showing the Nernst equation. Here we are being asked what the voltage of a voltaic cell is if it's made from solutions of tin 2 ions and tin 4 ions, and then indium metal and indium solution. So we set this up by doing our half reactions just like we've been doing. We do both reduction halves. So I'm going to start off with my more positive on the left-hand side. So I'm going to start off with my 10 plus 4 going to 10 plus 2. And my indium plus 3 going to indium. I did that with the goal in mind of making these two reduction halves. So I'm going to add 2 electrons to my tin, and I'm going to add 3 electrons to my indium. So then I look up on my reduction potential tables, and I find values of 0.154 volts and negative 0.338 volts. Well, we know it's not possible to have 2 reduction halves. One of these must be oxidation, so we always cross off the more negative or less positive, and we flip it. So now this becomes In going to In plus 3 electrons. And now that voltage is a positive value of positive 0.338. When we add these together, what we end up getting is a positive value. That was our goal. We get a positive cell potential of 0.492 volts. So we have that value that we're going to use in our Nernst equation, and we have to go through a balancing process now as well. So I look at this and I see that this is my reduction half, this is my oxidation half, and I've got 2 electrons here, 3 electrons here, so I know that I need to multiply this whole thing times 3 and this whole thing times 2. So when we go through that, we get 6 electrons plus 3 Sn plus 4s goes to 3 Sn plus 2s. And then we get 2 indium yields 2 In plus 3s plus 6 electrons. So we did that knowing that we wanted to get our electrons to cancel. That number of a 6 is going to be pretty important to us because that's going to tell us our end value. So we got our electrons to be equal so that they'd cancel. Again, I know that this is my reduction half and this is my oxidation half. Now what we can do is we can just go ahead and plug it into, actually I should go ahead and do the overall reaction. When I add all of this up, I end up getting 2 In plus 3 Sn plus 4 goes to 2 In plus 3 plus 3 Sn plus 2. Okay, so now that I've got my balanced overall reaction and I know my cell potential for standard solution of this, I can go ahead and plug it into the Nernst equation. I'm just going to try and leave myself a little bit of space here to do this. And I'm going to say that my value at these non-standard conditions is going to be equal to my 0.492 minus, this is going to get sloppy, I apologize, my constant over n, and remember we calculated that over here, n is equal to 6, times, and this is where it's getting really sloppy, this is all in the same line, times the log of the concentration of your products. So if you think about the concentration of your products, I'm looking now at my balanced reaction, my overall balanced reaction. My products are both indium plus 3 and tin plus 2. So I have to look at both of my products and I have to raise them to the power of their coefficients. So I'm looking at the concentrations raised to the power of their coefficients. So the first one I might look at is indium plus 3. I see up in my original problem that has a 0.5 for its solution concentration. So 0.5 and that's going to be raised to the power of a 2. And I'm going to multiply that times the concentration of my tin and my tin 2 ions, and it's tin 2, that's pretty important. If I look, I see tin 2 right there, which shows me that it's a concentration of 0.2 molar, 0.2, and we are going to raise that to the power of its coefficient, which is a 3 in this case. And now I'm going to divide all of that by the concentration of my reactants, which if I look at my reactants, I've got solid indium and I've got tin plus 4 ions. So only one of those has a concentration, just like we see in the problem itself right here. The concentration of your tin 4 ions is 0.1. So in that case, we're going to take 0.1 and we are going to cube it because we're going to raise it to the power of its coefficient, and there's only one coefficient, it's a 3. And the last thing now is we would just want to go ahead and write the shorthand notation for this. So remember, when doing this, we can write it the long way, or you can write it the long way, the shorthand way. So we've got oxidation, then reduction. So our oxidation half, you can look back at your half reactions and you see it's the indium. It's indium, it's metal going to ion, so it's your IN goes to IN plus 3, but it's not standard condition, so remember to write down your concentration, which is 0.5 molar in this case. And then after oxidation, you do your reduction half. So again, you can look back at your half reactions and see it's your tin ions, and you do your reactants, then your product. So it's going to be your tin plus 4, and I'm going to run out of room. You have to write down your concentration again, 0.1 molar, and we multiply that times, we don't multiply it, we then write our tin 2 ions and that concentration, which is going to be a 0.2 molar. I think that should do it.